Oh boy, a bench full of parts. What are we going to make today? Welcome to another All Nation line video. And in just a minute, we're going to discuss some of our power transmissions in our locomotives, a little bit of past history, and what we're doing today to improve the engineering. Stay tuned. In this video today, we're going to talk about the All Nation drives, past and present. We've been working to redevelop the drives and get those back out on the market, not only operationally, but for those modelers that need parts. So we've made quite a bit of progress recently, and we'd like to talk about the details of this progress today. Before we get into the mechanical engineering of the drive mechanism itself, it's fair to point out how power is implemented in some of the all-nation engines in the past. The modelers familiar with the all-nation engines such as the NW2 Switcher, the F3, F7 road units would have found, looking under the hood, several types of implementations. Before you would be an implementation where we had a tower drive with helical gears, or an implementation that used a chain drive on the tower. The older motors were of the open frame permanent magnet motors, which we have several of. They were high torque motors in their day. And there were various versions. Even ran across some that were similar from Central Locomotive Works in the past. But this would provide the power to the drive mechanisms. And so it would be a matter of how it was implemented. Modelers would note in the past that the All Nations over the years went through various types of implementations, and some of these parts may be recognizable to the modeler that may be found in some of our older equipment still in the field. And some implementations were ideal, others were not too satisfactory, such as the plastic tubing here, which I never cared for, and a lot of times you had repair issues. So today we have better techniques and more modern technology to build a better drive mechanism, and that's what we're going to talk about today. So what we're going to focus on today is shown in this mechanical drawing, which was used in our engineering department for reference use. It was the original drawing that did not contain any metrics and was done in December of 1948. The part numbers that were assigned are still applicable today. The general structure that is shown in this mechanical drawing is still the same today, with the exception of maybe on some of our tower drives, they went to a helical gear. And we're going to focus on the tower section. In this particular component that's driven from the tower, transmits power to the other wheel set. Here are the two main components that were original mechanisms that were delivered in the power assemblies for the model engines at All Nations. On some of our engines, both trucks could be powered. So in one type of implementation, you would have two tower drives inside the F unit, one on each end or one for each truck, or you could have a tower drive on one end and a universal drive connection to a power setup such as this that would go through the fuel tank or underbody from the tower drive that may look similar in connection to this, but with an extension that would allow you to connect universals and have an underbody transmission of power to the other truck. Like any mechanical implementation where you have gears, worm drives, or worms and gears, there are standards that are followed in order to make those mechanisms work smoothly without binding or having excessive wear. When these were assembled, you will note that the spacers or bushings on our drive shafts were actually pressed and spread like a rivet to hold the two side panels together. The smaller one is just a smaller implementation of the tower, same exact design and dimensions for a lower profile power truck. The disadvantage of this type of implementation is the fact that it's not easily serviceable. Even though these drives lasted many, many years and modelers got good operation out of these, you couldn't really easily take them apart and service them if, say, one of your spacer bushings started wearing or you started getting a noisier drive due to wear or even binding at some point because something is not lining up correctly. So they were a solid design, and I suppose from an assembly standpoint, it was quicker to stamp these instead of drilling and tapping. One of the other implementations that we went to was to have a servo link configuration of using a plastic chain drive, which significantly quieted the operation down compared to a Helix gear implementation. We're going to show you what the inside of the tower drive looks like when you take off the side. And here we can get a good shot of it. When we ground off and we're able to remove the side, you can actually see the inside of how this is mechanically put together. So the top shaft has a C-ring here that's inserted into a slot on the shaft to keep it from moving back and forth. And like most implementations, you're going to find maybe shim rings here or thrust washers here, or even on your axles. And that helps because on a Helix gear, you can have a lot of torque, and thrust washers help alleviate that problem. So the next thing we'd like to show you is how we're changing things up a little bit. One of the first things I decided to try to do was to create these side panels that hold the spacers and the bushings and the whole mechanism together, create those in polycarbonate instead of using steel. The steel sides were stamped with one of our dies, and I think by going to a polycarbonate, it'll help reduce the noise of the mechanism. It will not necessarily have a soundboard to amplify it like maybe a piece of steel does when your gears start getting worn. You will note, and I'm pointing this out because I am thinking about coming out with these mechanisms in a kit form for the modeler to assemble rather than pre-assembled. And I think it's good to be able to put something together like this, so if you do have problems, you can easily resolve the problem, particularly if you've been driving your mechanism for 5 or 10 years and it's starting to have some issues. And of course, the most important thing on mechanisms like this is to keep them well lubricated. The next step we decided to do was to use these brass bushings or spacers, which is part number 4040 in our diagram, and drill and tap each end. And we can put either a 256 screw in or a 348 with a lock washer, so that this allows easy servicing because you'll be able to take it apart and put it back together rather quickly. And I have the side panels laid out because in our development of the mechanism, our holes for the axle bushings are just slightly off center. So each of these pairs has to match up when they face each other. You can't flip these over because they will not match. Same for the smaller ones. And frankly, I'm not sure why that was done. Perhaps to make sure that your gear and your worm were aligned correctly, because it's very important that they are perfectly perpendicular when they are all assembled, and things aren't going to be going left and right and back and forth on you during operations. It would either give cause for wearing out your gears or locking them up. So the metrics on these for the holes and the spacers are exactly the same as were implemented in the original design of the mechanism. Another thing we went ahead and did, we 3D printed a little bottom plate here for snapping onto the bottom of this, and the sole purpose is to make sure that our bushings stay perfectly where they're supposed to in the side frames without doing any sort of major crimping or gluing or however they should be mounted. But secondarily, we think that maybe it'll help keep the noise level down, and when you want to lubricate it, it would give an oil pan for your bottom gear to constantly be picking up lubrication as it's operating. The wheel sets, of course, are the 40-inch wheels that go on here. One side would be insulated. There's quite a good number of parts and different shaft configurations. So if you're going to build a mechanism like this, you have to make sure you don't really need a long shaft on this end, but you need the shaft in the middle to connect up. And there's basically 3 different sizes of worming gears that we use, and I tend to just custom cut those myself. There's one more size here. Depending on where it's going to be used in the mechanism will depend on your length. And usually if you're going to have a drive under the main floor of your engine through the fuel tanks to the other truck, that length may be variable depending on your connections. So we'll try to make all the parts available so it's a rather easy means of bringing together all the parts to have a finished and operational piece of equipment. In almost all cases, our standard dimension for our shafts are 5/32. And of course, we always want a steel on a brass or phosphor bronze bushing, and not a brass to brass, as an example. Same thing where we have a steel worm, we have a brass gear on the axle. The axle typically is knurled. They could be drilled and pinned. That's a lot more work. Some fellows have even used some of the newer glues today to make sure that the gear is tightly bonded to the axle. I tend to like the knurling better. That's what we used in the past. The nice part about having a mechanism that you can put together and take apart without destroying it is the fact that you can fine-tune your mechanism with your thrust washer. So you can put it together. Typically, I mount these on a motor platform and break them in a little bit and lube them up, see where we're at, and then kind of feel if I need to put another shim in one of the locations, either in the worm or on the axles, and you can get a pretty darn good smooth drive. And once you're satisfied with that, you can put it all back together with the screws, and you'll have a finely tuned mechanism going forward. So here is our completed tower drive, all set to be implemented with the chain from Servolink. Everything is put together and manually tested for smoothness, making sure our worm gear shaft isn't moving back and forth too much, and it feels not too tight, not too loose. And the next thing to finish this is to put the wheels on, press the wheels on, and put the chain on, and it should be ready to install in a power truck such as the All Nations Blomberg trucks. We will be testing this to see if it'll work in a P&D truck as well. We know the wheels sets will work, but not sure we have clearances for our mechanism, and we will be testing that. This is a set of P&D trucks with just regular wheel sets installed in it. And if we can turn these support bars upside down, we'll have enough clearance probably for a tower drive and the gearing for the other axle. But we have to test that yet. These are nice trucks. They don't fit NRF units. They're a little bit oversized in width and length, unfortunately. But if you have other models where you can use these trucks they would work just fine. For my own modeling purposes, I've been experimenting with different power implementations and drive shafts to the tower drives. The 3D printing has allowed for easy experimentation to implement various types of motor configurations. I call it adaptive additive engineering. And in this model where we have the side cut out, we have a Pitman motor on a 10-degree angle with universal joints, a brass 5/32 shaft, and another universal joint through a bushing that connects to the tower drive that has plenty of play left and right. So when you're going around tight curves, you really don't have much of an issue. And this, of course, is implemented on our Blomberg truck. And we will hopefully be coming out with those trucks once we have all the parts sourced and the bearings. This is one implementation. Earlier, you saw the implementation that we did for a couple of switchers on our layout. Other implementations for configuring the CAN motors that are available today will include the following. We've been playing around and experimenting with syncing a Pitman motor into the fuel tank so that we could have a direct connection to a power truck without a tower drive. We'll be experimenting with that. Basically, the motors are sitting in the tank. They're mounted. This implementation here is where the motor sits on top of the frame and connects directly to the tower drive. And what we're trying to achieve that on both the underfloor drive and on the top is that the motor drive shaft is pretty well in line with the tower mechanism, so there's not too much of a issue with the universal joints, because I think the tighter the universal joints tend to turn, you can get a little bit of additional noise from that. So a more direct power mechanism is better, I believe. The fuel tanks, of course, are mounted with a couple of screws to the platform. These are designed so they just drop right into the F unit A or B without having any issues in terms of the width. It's just an easy mechanism to service overall. So we will be experimenting with this type of implementation to a tower and having a drive shaft from the tower to the other truck through the fuel tank. And again, 3D printing and some of this adaptive engineering work in CAD helps us develop stuff that we never could do easily before. So I hope you like this video, and I would say that if you're going to take one of our mechanisms in kit form, the first one you put together, you're going to play around with it for quite a little bit, maybe an hour or two, putting it together, taking it apart, and just getting familiar with it. But once you do one, it becomes pretty routine. And again, I think servicing these parts when they need servicing is what modelers do not have an opportunity to do with other mechanisms on the market. And everything is standard from the 5/32 shaft to the 5/32 axles that we have. And the flexibility is, I think, something that makes this a desirable component. And modelers have told me over the years that the reason they like the all-nation drives is they're pretty bulletproof. They give a long life of operation with very little trouble, as long as you keep them lubricated, and they're a good investment for your engines and your models. And these drive mechanisms, I have seen them implemented in AHM Fairbanks Morris units, and other fellows have put them in other types of locomotives where they need replacement drives, and they have worked quite well. But that borders on the line of kit bashing, you might say. And we will have all the components available, including extended shafts that you can custom cut to the length you need, and have readily replaceable parts when needed. So again, thanks for joining me here, and any questions, send me an email or give me a call. And if you think there's something to be improved, we'll definitely look into it and improve it.